Okay, so this right here is a spreadsheet that I made to kind of demonstrate the Euler's method um, without having to do it by hand. And I'd like you to use this spreadsheet for your project. I don't want anyone to break the spreadsheet that you all can download. So right here is a thing that says make copy to edit. So if you want to make your own spreadsheet, what you should do is just go to File, Make a Copy, and then it'll open something new. It'll ask you to give it a name. And it's really thinking hard about that. But it'll make you your own copy that you can edit. This one will be protected from anyone changing it. And then there are going to be figures for our solutions in the second tab, but you'll see that later. So this spreadsheet is set up for the logistic differential equation that dn dt is equal to Rn times k minus n that we worked on in class. During your project, what you'll do is you'll change this to the differential equation that you use. So just kind of follow me through how this one works so that you can make sure that you know how to change it for your problem. And given an initial condition with T0 plugged in here and N0 plugged in here, the spreadsheet is going to accomplish the goal of solving dy dx equal to f of xy using Euler's method, where you approximate y at the next step by y at the current step plus h times f. I'll talk about what you should do with this later. Right now, I'm just going to explain how the spreadsheet works. So like I said, you plug in your initial value T0 and N0, it's like your X and Y. And then since the logistic equation has R and K parameters, I made them something that you could change up at the top of the sheet. And then you also have to plug in the step size. So here's that H equals 1 that we were using in the previous problem. And so in this first column right here, what it does is it calculates the different, like x's. So I called it tn, or I called it xn, but yeah, anyhow. So the first one is equal to C6. So it just pulls in that T0. And then the next one takes the previous value right up above it, C11, and then adds I6, the step size. Now what's important is that when I use something that I want to always pull the same value, I use these dollar signs. So $I, $6 means even if I copy this formula to a new cell, always refer back to I6. And then once that formula was plugged in, I can just, here, I'll actually delete these things so that they're not there. Whatever, that's enough to delete. So those things are empty, but I wrote this formula right here, and then I can just drag the formula down. It takes a second. And the next one down will say, okay, the next x, so that was like x0, x1, so now x2 is going to say, I look at x1 right up above me, and then I add h always. And then you go down to x3 and it does the same thing, so on and so forth. Then after that, I made a column that calculates the f at each step. So we're going to look at this formula real quick, just make sure we understand all the pieces. So this is calculating my derivative. It says I'm going to look at the r value in f6 times the times the current y value right next to me, times the difference between the k value and the current n value right next to me. And then that is the same as dn dt equal r times n times k minus n. Again, the dollar signs mean always refer back to the same place. The ones without dollar signs mean I'm going to drag this cell down and then I want you to update differently in the future. So all these numbers look the same because it doesn't have a million decimal places. So that's f of, so that's f of x0, y0, basically right there. And then I went ahead and dragged this whole thing down before, but now in the next step, that f of x1, y1, kind of what you're seeing is it still has that r times, now I look at my y1 value times k minus my y1 value. And if you go down the line, it continues to do that. And then the actual like Euler's method update is this first cell pulls in your y0. And then the next one says, okay, my current value is y0 plus h, always pull that, times the f value you calculated at y0. And then in the next step, it's, okay, to find y3, I look at y2 right there plus h times the f calculated at y2. And that thing, I drag down the column to populate it, but it's not really important that you see that more than once. As long as you know that that's a thing, you just drag and the formula extends. In this column, I just have the times again, the, x1, x2, so on and so forth. And then right here, I've written the solution for the differential equation that we had. So you don't know how to solve the logistic equation, you'll learn that real soon, but I wrote it here so that we could calculate errors, with absolute error just being the difference between the real answer and our approximation. Real answer and approximation. I really hope you can see my mouse when I'm pointing with these things. And then relative error being the absolute error divided by our real answer. So all that stuff is calculated right here. When you're doing your project, what you're going to do is right here in rows 5 and 6, I guess, that I've highlighted in red, that's where you're going to put in your own values. So you'll have a different differential equation, you'll have different initial conditions and different like parameters that you plug in. And then in the blue area that I've highlighted, this column right here is where you're going to have to write the f for your differential equation. And you'll just type it in the same way that I kind of talked through. Mine is just copying the logistic. Yours will be copying a different thing, and then you drag it down. And then your formulas for x and y, the like approximations, actually don't need to change. The last thing you'll have to do is just type in your own solution right in this cell and then drag it down. So I'll open up your project and show that to you next so that you can kind of like see the differential equation I'm talking about. But for now, after you've updated it to have everything that you want, on the second tab of this sheet is going to be figures, and they'll automatically update. So it gives you the approximate solution in the first plot. That's just like your y1, y2, y3, so on and so forth, and your true solution, that curve that you don't actually know how to calculate. And then I have it plotting the relative error right here just so that you can see what happens. So if I kind of like go back over here, I can change to, let's see, we said when we classified this differential equation that a logistic solution heads towards its carrying capacity 0.5. So I start at 0.1 down here, and then I head up to 0.5. So a quick thing to do would be to say, okay, what if I start at 0.9? It's going to update everything in the sheet. And you see that now my derivatives are negative, so I'm decreasing my solution. And we can see that, yeah, I start at 0.9 and I head down to 0.5. So once it's set up, it'll just kind of like change itself. You can change the step sizes. So let's say I want to see further in time, so I make my step size bigger. That was not good enough for what I wanted to show you. Take my step size to 10. There we go. That's the start of a problem. So now you're not seeing that nice smooth increase up to 0.5. There's this weird jagged thing that shouldn't occur. Let's take this even bigger, making it even worse. See, I took h equal to 15, and now this doesn't look anything like the solution to the logistic equation should. And that's just demonstrating to you that if your step size is too big, your solution's going to be bad. So that's how to use the spreadsheet. In the next video, I will show you the document for your project, and then we'll do our wrap up.